as I'm looking at, a fan curve, and I just took a snapshot, common fan curve here, let's define what's on the screen. First thing is across the x-axis, the horizontal, that's our volumetric flow, right? Cubic feet per minute. That's how much air we're going to move. On the primary axis for y is our system resistance, right? This is the amount I am fighting against, or I'm trying to overcome that pressure. And lastly, on the other side, we have a secondary axis, and that's got our brake horsepower scale. So right off the bat, there's our axes. Now let's kind of get into the meat and potatoes. The red line or the red curve on the screen, right? This is known as the fan curve, right? And the fan curve, this is rooted in test data, right? We took this fan, we put it in an AMCA test chamber, and took all the values and found the relationship between static pressure and CFM, right? And it makes sense. The lower the static pressure is, the higher the airflow. As static pressure goes up, airflow is going to drop, right? So the shape of that red curve makes sense. And this is represented from data at a specific RPM, right? Now, another thing you can see right on the screen, I wrote 1448 fan RPM, FRPM. Terminology again. RPM is typically what the motor is turning. When you see fan RPM, that's what the impeller is turning, right? So anytime you see FRPM, if it's a direct drive, that is the same RPM as the motor. If it's a belt drive, that is showing you your relationship through the pulleys and shivs between the motor and the belt. All right, so we have a fan curve, which is that red line, our fan RPM, but we also have this blue kind of a squared looking parabola, right? And this is the system curve. This represents all the duct work, the 300 feet, the 6 elbows, the reduction, all that has been added up, right? How much system resistance is going to be added to the system to overcome in this entire system, right? And that is represented by that curve. Now, the neat part is where they intersect, the system resistance curve and the fan curve, that is called the operating point. So whatever fan we're looking at this RPM, at this static pressure, will move this amount of air, right? And how we read this, we got one more curve, the brake horsepower curve. And brake horsepower is really recorded as we're testing to find our CFM static pressure relationship. We're also taking data points. So how much horsepower did it take at that point to move that air? Now, a brake horsepower curve, that's the black dashed, that can be above the operating point, below the operating point. It actually has no correlation to the fan or if it's a good or bad selection. It's just depends on the scale to the right-hand side, right? And when you read the brake horsepower curve, the key is that you go from the operating point and you draw a line up or down until you hit the brake horsepower curve, and then follow it across that secondary axis, right? So in this scenario, we're, to move 1200 CFM against 2 inches of static pressure, that's our operating point, it would require 0.85 brake horsepower to do this, right? So you can assume we're going to have at least a 1 horsepower motor in this application.